Hello, we are going to cover the first part of chapter 9 in this video. It's going to cover sections 9.1 through 9.4. There are 12 reactions in total for this chapter, and in this video we're going to cover just the first one. So we're going to start by doing a little bit of background information. We're going to look at what makes up a triple bond. So this chapter is all about alkynes, and so we're looking at what creates an alkyne and the arrangement around it. So that means that we have to have a triple bond, and when we have a triple bond, it's made up of one sigma bond and two pi bonds, and the carbons that are in it have an sp hybridization, which means that they will have a linear shape and a 180-degree bond angle. So here's our kind of bubble picture of that. The gray in the middle is that one sigma bond, and then our pi bond, we have one p orbital going up and down here. So we have the overlap on the top and the overlap on the bottom, and then that second p orbital is kind of going towards the front and the back. So we have the orbital in the front overlapping and then in the back overlapping, and so that gives us our triple bond. The one sigma, the pi that's below and above, and the pi that's in front and in back. Triple bonds are the shortest and the strongest bonds compared to double and single bonds. Because it is a linear shape, the smallest ring size that can have is a 9 carbon ring. So this is called nonine. So known for the, well, cyclononine, known for the 9 carbons, and then we end alkynes with -ine. We'll talk about nomenclature here in a few slides. And then the last thing I want to mention about this before we move on is that because it does have these two pi bonds, a lot of the reactions we're going to talk about are very similar to chapter 8. They're very similar to our alkene reactions, and that means that our pi electrons can act as a nucleophile and as a base, depending on the situation. So we do like to connect it to the real world, of course, and so here's our couple of examples. Alkynes can be found in nature, so the example here is this molecule, and it's found in leaves and flowers and plants throughout North and Central America. The name of it is ichthyroethol. I probably did not pronounce that right, but it translates to fish poison. So it literally does kill fish, and it actually kills or harms a lot of other animals. It's the same chemical that's in dahlias and a few other plants. So it's one of the reasons why some of our plants can be harmful to cats and dogs. And then in industry, one of the common ways we see alkynes used is in acetylene, which is a carbon-carbon triple bond with one hydrogen on each side. So its IUPAC name would be ethine. It's used in welding, and it's also used as a starting material for a lot of other molecules because it's so reactive and it's so small. So we are going to talk about nomenclature. Now, as I mentioned in our last chapter, when we're dealing with nomenclature with a functional group, nothing is changing for what we've already learned. We're just adding on. So the same rules as before. We're going to find the longest chain that includes that functional group. So this time our functional group is our triple bond. We're going to name our substituents. We're going to use the lowest numbers possible. And remember that our triple bond, because it is a functional group, gets priority, meaning we number the chain in a way that gives our triple bond the lowest number possible, regardless of what numbers our other substituents get. We're going to put everybody in alphabetical order, and then because we are naming alkynes, the ending of our name will be -ine, Y-N-E. And so a couple examples here. Here's our chain. So our longest chain with that triple bond is a 7-carbon chain, and we number it starting on the left over here so that our triple bond is at carbon number 2. Even though all of these other substituents are over here, we want to give that triple bond our lowest number. So we would call this 5,5,6 trimethyl because of all those methyl substituents, 2-heptyne, or we can put the 2 in the middle and call it hept-2-ine. So very similar to our alkene naming. The example up here is reminding us that that triple bond needs to be part of the parent chain. So if we numbered it straight across, 1, 2, 3, 4, 5, 6, 7, 8, it would be an 8-carbon chain, which is longer than the 7-carbon, but that 8-carbon chain does not include our functional group. Keep in mind. All right, we are going to do a couple practice ones here. And then we're going to draw out the one that we have a name for. So I have my triple bond here, which is a good indication that we should start numbering from the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we have something like a triple bond, it makes numbering pretty easy because we know exactly where we need to start. So we have a methyl, we have a methyl, we have a chloro. Chloro is going to come first alphabetically, so we're going to call this 5-chloro 2,7-dimethyl. And then I have 9 carbons with that triple bond. So it will be no9, but we have to say where that triple bond's located. And so it starts at carbon number 3. So we're going to say 3-no9, which definitely sounds very weird, but it is correct. All right, let's look at our next one here. So same idea, we have that triple bond, which means we want to start numbering it from that left side because that will put our triple bond at the lowest number possible. 1, 2, 4, 5, 6, and then I'm going to go up because that will give me 1 extra carbon. 7, 8. We have a methyl. We have an iodo. So iodo comes first alphabetically, and I definitely need to have some stereochemistry information there, so I'll leave a little space. 2, iodo, 6, methyl, pretty much ran out of space there. And then we have octyne with a triple bond at number 3. And then if we check our stereochemistry up here, our iodo is going to be the highest priority, triple bond will be second, methyl's third, so 1, 2, 3, we're going to the right. So I am going to add in 2R, and I do need to add 2. Carbon number 6, so a stereocenter. We're not given any dashes or wedges though, so we don't know if it's an R or an S, so we can't include that in the name, but we do need to include a 2 right there to specify where that R is located. All right, last one, we're going the other direction. We know the name and we want to draw out. So we kind of start backwards. We know it's 7 carbons, and we know that it has 2 triple bonds. Diene is telling us that there are 2 triple bonds. So I know that if I have 7 carbons, I'm going to do 1, but then carbon number 2 is where my first triple bond is. So drawing these is a little bit trickier because we should have that linear shape when we draw it. So 1, 2, 3. And then carbon 4 is my second triple bond. So 1, 2, 3, 4, 5, 6, 7. And my last couple can have our zigzag shape. And then carbon number 6 will have a bromine. So 1, 2, 3, 4, 5, 6. And we're not given any stereochemistry information for that bromine, so we're going to just draw it in there with a line. Last thing I want to mention with the nomenclature is we won't have easy cis strands with our alkynes because it is that linear shape. So there is not any there's any other way to draw it. It's only just a straight across shape. Okay, so let's move on here. In order to talk about the reactions in this chapter, we do need to talk a little bit more about how reactive and our alkynes are and in what way. And we're going to start by talking about terminal alkynes. So a terminal alkyne is when one of our carbons is only bonded to a hydrogen. So let me draw something for us here. Maybe. Let's see. Oh, there we go. Okay, so if we have a structure that looks like this, so carbons coming off of each side, this is called internal alkyne. So meaning that it's not the end of the structure, it's somewhere in the middle. But if we have a structure like this, so triple bond, but then one of the sides just has a hydrogen coming off of it, that is a terminal alkyne. And so we use this really just as a way to describe where our triple bond is located, but it also helps us talk about how it's going to react and what kinds of things will form because of that. So let's look at the acidity within this structure. So we have 3 carbon-based compounds here: ethane, ethene, and ethyne. So I did say different names than what's on the screen because what's on the screen are their common names, but ethane, ethene, and ethyne would be their IUPAC names. We have their pKa values. We know that as pKa gets smaller, our structure is becoming more acidic. And so the question is why? Why is an ethyne more acidic than the other two? And if we think back to Oreo, A doesn't matter, they're all carbons. R doesn't matter, there's not going to be any resonance. I know there's double bonds and triple bonds, but if we remove that hydrogen and create its conjugate base, that lone pair is right on our carbon that is part of our double or triple bond, so it wouldn't be able to have resonance. There's no induction, there's no electronegative atoms in any of these, so that leaves us down to O for orbital. And what the orbital tells us is that we are looking at sp versus sp2 versus sp3 atoms for these 3 different structures. And our ethyne has that sp hybridization, which means it has more S character. It's a 50-50 mix. And so because of that, when it's in its conjugate base form, that lone pair is going to be held closer to the nucleus, closer to the protons, which means it's going to be more stable. So remember, Oreo is all about deciding which conjugate base is the most stable, because that's going to tell us which acid was the strongest. So our terminal triple bond has the most stable conjugate base, which means it is the most acidic. We still are going to need a very strong base to remove that hydrogen. So let's look at a couple options. So we have 2 different options here. We have NH2 negative, and it just has a sodium here as a counter ion. And we are showing the proton transfer mechanism. So we're going from that lone pair to the hydrogen, and then we're breaking the bond, putting that lone pair onto the carbon. So this is our base, this is our acid. Our conjugate acid is NH3 ammonia, and then here is our conjugate base. The other example that's shown on here is using hydroxide, so sodium hydroxide. Same mechanism. Our conjugate acid is water, and then here's our conjugate base. Now, notice that our equilibrium arrows are favoring opposite sides. The one on the bottom here is favoring the reverse direction because the conjugate acid that was formed during the reaction is stronger than the acid that was started with. And so because of that, it's not going to favor the direction we're looking for. But if we start with a stronger base, the conjugate acid that we form will be weaker than the acid that we started with. So NH2 negative is going to be a very good option for us for this. Another option that we can use, sorry, I'm trying to switch over to my pen and it is not happy with me. So another option, oh gosh. Here we go. Another option is to use H-, which is a hydride, and so we'll see this in the form of NaH, so sodium hydride. And then another option would be have some type of alkane that is negative. We already know that an alkane is going to be a weaker acid than our alkyne. So this is one option. And again, we might see it written as a sodium alkyne. So a couple different options there. So this does take us to our first reaction in the chapter. Again, I'm using the numbers that are in the summary at the end of the book. So it actually means that we're going to go through the reactions not in numerical order for this chapter, but we're going to go, let me start that over. We're going to go through them in the order that they are presented in the book, but that is not the same as the numerical order that they are listed in at the end of the chapter. All right, so reaction number one, the title of this section is Preparation of Alkynes, so this is how to create alkynes. So we are starting with a dihalide, and if we react it with a strong base, we will get our alkyne. So we're starting with a dihalide to create our alkyne. Here is our mechanism. Now notice that it's an E2 mechanism. So we're going to take our base, we're going to remove that hydrogen, the electrons will fall in to create a double bond, and our bromine is our leaving group. So we're doing a proton transfer and loss of a leaving group at the same time, and then it happens one more time. Our base takes off that hydrogen, our lone pair or our electrons there create the triple bond, and we have that loss of a leaving group. So this is back-to-back E2 mechanisms. I want to do one more little piece of information to have some summary information here. So with our reaction, there's one more way to draw this out. So the way that it's drawn here, this is a geminal dihalide, which means that our two halogens are on this, so like Gemini twins. The other way to draw it out would be to have our two halogens on neighboring carbons as our vicinal dihalide, and either one will give us the same product. And then the base that's being used here is that NaNH2. It does need to be a good, strong base. I think that is it. Oh, wait, I do have one more thing to add on here. If it is a terminal alkyne, then we would want to have our, excuse me, we would want to add in water as a second step. So let me draw that out for you. I'm going to get a smaller, here we go. So if we have bromine and bromine, here's my arrow. In that first, I would have Na, I see this written as NaNA2 exciv. So S, just meaning that we're going to have extra of it, because we would need to have two equivalents to do the reaction twice, but it might be written as XS, meaning you have excess. And then 2 would be to add in water, because that NaNH2 will remove our hydrogen off of our triple bond, and so the water will replace it. Oh, that got rid of everything. I meant to hit erase to erase that last little mark I made, but it deleted everything. I am sorry about that. Let's see if I can undo it. I don't think I can. Oh, there we go. It's back. Thanks for sticking with me through this one, guys. Okay, so here's our 4-carbon chain. Our 2 bromines get removed, as well as the 2 hydrogens, and we end up with our terminal alkyne. And the hydrogen that's on the here is replaced with that water because that NH2 will remove it. So the water is needed if being a terminal alkyne. There we go. All right, that is it for this video. Thank you.